It's your boy AC. Alright, my friends, let us begin this video. So number one, we want to learn what the definition of continuity is, and in a weird way, we've already kind of looked at this 100 times in the limit section, but let's actually define it. So in calculus, this is the definition: a function f is continuous at c if the following three conditions exist. Okay, so if f of c is defined, well, this is basically saying, does the point exist, right? When you plug in the x value, do you actually get a y value? This says, does the limit exist, right? Well, it doesn't have the plus or the minus, so this means from both sides. That means, do we approach the same y value from the left and from the right? And this says, well, if the point exists and the limit exists, okay, is 1 and 2 equal to each other? So are they equal to each other? Okay. In other words, in kind of a weird way, if you have any holes, any vertical asymptotes, anything like that, it's not continuous. Okay, and let me show you why. Let's look at over here, which is the problem number one. This violates definition one because, well, what does the point say? Is the point defined? Well, at f of 2, it does not exist. It is undefined because at 2 we have a hole. Done. It's not continuous. So you see, if you have a hole in a graph, you're not continuous. Let's go to definition number 2. Okay, definition number 2. This says a function is continuous if the three conditions are met. Well, does the point exist? Well, in this scenario, the point does exist. F of 1 does equal 7. The point does exist, right? Because it's filled in right there. But now we go to number 2. Does the limit exist? Well, my friends, the limit's not going to exist because the limit as x approaches, in this case, 1 from the left, okay? Oops, the limit from the left is 7, okay? And then the limit as x approaches 1 from the right is 5, right? And these are not equal to each other. So the limit, so we know then the limit as x approaches 1 of this function does not exist. Okay, and let's look at definition number 3. Okay, well, we always ask ourselves, does the point exist? Well, in this case, f of 1 is equal to 7. Boom, we're golden. All right, well, does the limit as x approaches 1 from the left of our function equal the limit as x approaches 1 from the right of our function? Well, in this scenario, as you approach it from the left and from the right, we approach the y value 5. So the limit does exist and the point exists, right? Now, condition number 3 says, well, if they both are defined and they exist, they have to be equal to each other. Well, I'll write it over here. Well, f of 1, the point is 7, and the limit that we concluded is 5, right? They're not equal to each other. F of 1 does not equal this limit. Okay, they need to be the exact same y values, right? This is 7, this is 5. They're not equal to each other, so that violates definition 3. So this is not continuous, right? In order to be continuous, we need to just have a graph like this. Notice that anywhere on this graph, there's no holes. It does not break or anything to that extent. So let's look at this over here. Okay, and I'll choose, I haven't used the color brown, so let's use the color brown. All right, it's your boy AC. Let's look down at the graphs below and determine whether they are continuous or not. Justify your answer. Is the graph the left? All right, I spelled the graph. Is the graph to the left continuous at x equals 3? Justify. Okay, well, the first thing I want to ask myself is, does the point exist, right? Does f of 3 exist? Well, they're both open circles, so this does not exist or non-existent. You'd like to use either one. There it is. Okay, since f of 3 is not defined, okay, the graph is not continuous. Boom. Okay, there it is. Okay, the function below is f. Determine all the locations that the function is discontinuous. Well, I know this function is not continuous, okay? And let's go ahead and say this in the interval. Let's actually make an interval. In the interval, okay, we're doing an interval of -2 to 11. Okay, just so that you know, we're going to look at everything in between these two endpoints. So the function below f determine all the locations that the function is discontinuous between these 2 points. Well, I know it's not continuous here, so at x is equal to 4, it's not continuous. I know it because there's a hole, but really the limit from the left and the limit from the right don't exist, so we're golden there. And I know it right here at x equals 9, it's not continuous, all right, because we have a hole there, and we know at x equals 9 then that the point is undefined, so this is not continuous. Okay, and that's really how we work with this. That's the definition of continuity. We need those 3 things to exist in order for a function to be continuous. So let's look over here. The function below is f. Determine all the locations that the function is discontinuous. Well, number 1, okay, at -3, does the point exist? Well, no, we have a vertical asymptote, right? You notice right here, you don't exist at vertical asymptotes, right? So this is non-existent. So we can conclude at x is equal to -3, it does not exist. It is discontinuous or not continuous. And I'm being really sloppy with my justifications here, but I'm just trying to get you the idea for the main big picture that we're going to look at later. And right there, I know this is not continuous because, well, first of all, ask yourself, does the point exist? Well, the point does exist, right? Because there's a filled in circle there, which is -3. Does the limit as x approaches 2 from the left and from the right exist? Well, they do, right? The limit means you approach the line. We approaching 1. But remember, condition 3 states that they have to equal to each other. Since f of 2 does not equal the limit as x approaches 2, we can conclude that the limit does not exist, right? Or sorry, that f is not continuous. And later on, I'm going to show you how to really justify these perfectly, but I'm just wanted you to make sense of this graphically, okay? So let's go to just 2 multiple choice questions that I wanted to look at here. It's your boy. Let f be the function given by this. For which of the values of x is f not continuous? Well, ask yourself, what are ways in an equation, how can we tell when a function is not continuous? Well, we're not going to be continuous when there's holes or vertical asymptote. And anytime you can get 0 over 0, right, this is going to give you a hole. Okay, anytime you can plug in some number for x and your equation is there's a hole, or if you can plug in some number, I'll call it a, and you get some number on the numerator divided by 0, well, can you divide by 0? No, that's a vertical asymptote. So anytime you get 0 on the denominator, it's not continuous, okay? So if we look at this function here, well, I know I see the same factors on the top and the bottom. That's going to tell me if I plug in 3, I'm going to get 3 over 3 minus 3 on the top, which is 0, and then 3 minus 3 on the bottom, which is 0. We're going to get a hole. So we know we're not continuous at x equals 3. And on this bottom portion here, we get x is equal to, well, what do you need to plug in here to get 0? Well, -1. And is there another x plus 1 on the top? No. So when you plug in -1, you're going to get some number. Well, -1 plus 1 on the bottom is 0, and you're going to get a vertical asymptote. So we know at -1 and 3, which is right here, our function is not continuous. Wonderful. All right, and the last example I wanted to go over was this limit problem here. That graph of f is shown above. Which of the following statements is false? Well, does the limit as x approaches 2 exist? Well, here's 2. Well, the limit does exist because we approach the y value 3. Remember, limit is what does the y value approach, okay? So we know this is a true statement, so we can get rid of that one. Does the limit as x approaches 3 of f of x exist? Well, this is telling us that it does. Well, the limit as you approach 3, well, yeah. If you approach 3 from the left and from the right, you get the same y value. This is a true statement, so let's get rid of that. And let's go to limit as x approaches 5. Well, as you approach the limit from the left and from the right, you get different y values at 5. Ooh, so I know that this is false, right? So I can immediately conclude it's got to be C. But if you go over here, okay, let's go to D and E. The limit as x approaches 7. Well, as you approach 7, the limit does exist. You get the exact same y values. This is true. Oh, and I do have to make a correction here, okay? The function of f is not continuous at x equals 2, okay? Which of the following statements is false? We're trying to figure out which of the following statements is false. Okay, well, the function of f is not continuous. Well, are you continuous here? No, you're not, because you have a hole. Remember, anytime you see a hole, you just can know it's not continuous. Now, which by definition does this violate? Well, it would violate definition 3, because the point does exist. At f of 2, it is equal to 1. And the limit as x approaches 2 from the left and from the right. Okay, I'm writing this really sloppy, but from the limit as we approach 2, the limit as we approach 2, well, oh, look here, as we approach 2, the y value is 3. They approach 3, right? So this exists, but are they equal to each other? No. You have this point needs to equal your limit, and it doesn't, right? We get 1 here and we get 3 here. So we know that the function is not continuous. This is a true statement, right? So we can get rid of these and you're left with C there. Pretty tricky stuff, but I hope this is helping you to understand what it means.